Welcome to The Explainer. Today, we're diving deep into a world that sounds like it's straight out of science fiction, but it's happening right now, inside people all around us. We're talking about biomaterials, these highly specialized agents designed to go on a mission inside the most secure, complex environment on the planet, the human body.
Think about it. What if you could replace part of your body? For a lot of us, this isn't some far-off idea. It could be something as common as getting contact lenses to see better, or something as life-changing as a hip replacement. All of these incredible solutions depend on sending a foreign material on a mission inside of us.
So every good mission needs a briefing, right? Let's get into it. What exactly is the assignment for these undercover agents we call biomaterials?
Okay, so at its core, a biomaterial is really just any material, whether it's man-made or from nature, that's been engineered for a biological job. Think of a contact lens. It augments your vision. Or a hip implant. It replaces a joint. Its whole purpose is to get in there, integrate as smoothly as possible, and get the job done without causing a scene.
Now, you can't just send any old material on this mission. The absolute #1 credential, the first thing on the list, is biocompatibility. And that really just boils down to, how well does this material get along with the body? Is it a friend or a foe? The body has to be able to accept it, so it absolutely, positively cannot be toxic.
And this brings us to the very first test every single one of these potential agents has to pass. It has to prove it is not cytotoxic. If a material goes in and starts killing the body's cells, well, the mission is failed before it's even begun. A good biomaterial has to be a friendly agent. It has to be cytocompatible, which just means our cells are totally safe around it.
All right, so once an agent with the right credentials has been chosen, it's go time. It's time for insertion. This is first contact, the moment that biomaterial goes behind enemy lines, so to speak, and faces a whole gauntlet of challenges.
The second that material crosses the threshold into the body, alarms start blaring. You have to understand, the body's immune system is this incredibly sophisticated security force. Its main job is to find and neutralize anything foreign. It doesn't know this new thing is there to help. All it sees is an intruder that does not belong.
And the body's response is lightning fast. We're talking milliseconds, literally, in the blink of an eye. Proteins just swarm the material, coating its entire surface. This new protein layer is like a giant red flag, signaling the immune system's security guards, the white blood cells, to rush to the scene and check it out. This kicks off inflammation, and it can all end with the body deciding to just wall off the intruder for good.
And this right here, this is the ultimate risk of mission failure. If the body decides this agent is a threat that it can't get rid of, it does the next best thing. It builds a prison around it. It creates this thick, scar-like wall called a fibrous capsule to completely isolate the implant. And for the person with the implant, this can mean pain, problems, and a total mission failure.
So given all these intense challenges, how on earth do scientists and engineers choose the right agent for the job? Well, the answer lies in understanding that there are different classes of agents, and each one has its own unique skill set.
So let's look at the main toolkit. You've got your metals, which are the strong, lightweight operatives. They're perfect for heavy-duty, load-bearing missions like hip implants and bone screws. Then you have ceramics. These are the hard, super low-friction specialists you want for things like joint surfaces or dental implants. And finally, you have polymers. These are the versatile jack-of-all-trades agents, sometimes even biodegradable, used for everything from dissolving stitches to really advanced drug delivery systems.
But here's where it gets really, really cool. The cutting edge is in what we call biofunctional materials. Think of these as master spies with perfect forged credentials. Their surfaces are engineered with special molecular signals, like this RGD sequence, which is a pattern our own cells use to talk to each other. It's like having the secret handshake. It tricks the body's security into not just putting up with the agent, but actively welcoming it and integrating with it.
Speaking of perfect agents, nature has actually already designed one that honestly puts a lot of our own creations to shame. It's a material with properties that are almost, unbelievable.
That's right, spider silk. For centuries, we've known it was beautiful and incredibly strong, but as a biomaterial, it's in a whole other league. It might just be the ultimate natural operative for missions inside the body. I mean, just look at its resume. It is unbelievably strong but also flexible. It's got this smooth surface. But its real masterstroke? It's practically invisible to our immune system. It just doesn't set off those security alarms. On top of all that, it biodegrades at a super slow, controlled rate, which makes it perfect for missions that need to last a long time.
So, if it's so great, why isn't it in everything? Well, here's the catch. You can't really farm spiders. They're territorial, they're cannibalistic, it's a non-starter. But the solution is just brilliant bioengineering. Scientists have managed to take the genes that code for spider silk and put them into bacteria. They've turned these tiny little microbes into microscopic silk factories, making it possible to produce this super material at scale.
Okay, so let's bring this all back to the real world for a minute. Because even if you have the absolute perfect material, a successful mission really comes down to overcoming some really fundamental engineering challenges. One of the biggest issues is what's called mechanical mismatch, or stress shielding. So imagine you put a super stiff metal implant right next to a more flexible piece of bone. That metal is so strong it ends up taking on all the load, doing all the work. The bone around it? Well, it has nothing to do, so it gets lazy and starts to get weaker. It's the body's use it or lose it principle in action, and it can actually lead to the implant failing. The agent's properties have to match the local environment perfectly.
But before any agent, any material can be deployed, it has to pass one final, absolutely non-negotiable test. It has to be perfectly, spotlessly, 100% clean. And this leads us to the sterilization dilemma. You have to kill every single microbe on that implant. And the common ways to do that involve pretty harsh methods: intense heat, high pressure, reactive gases. The problem is, those very same methods can actually damage the biomaterial, changing its properties and compromising the whole mission. It is an incredibly delicate balancing act between making it safe and preserving its function.
And all of this brings us to our final question, which I think really gets to the heart of it all. When you consider everything we've talked about, from the body's aggressive security system to the tricky business of sterilization, what do you think is the single greatest challenge in preparing these agents for their mission inside us? And more importantly, why do you think so? It's a huge, complex problem, and there's definitely no easy answer.